So record. All right, so we are backing up from 10.3 to 10.2 for a moment because there were some problems with Activity10.2B, the interior angle sum. And perhaps my instructions left something to be desired. So let's go see my instructions. All right, so the purpose was to explore angle concepts related to polygons, in particular the sum of interior angles of any polygon. And then materials were supposed to be the pattern blocks or some pattern block app. So if you didn't have pattern blocks at home, which most of us don't, I listed 2 pattern block apps to play with. And now we have a new ding dong that tells me when someone joins, because my other class has 40 students, and if I don't turn that bell on, Canvas doesn't tell me somebody joined. Kayla, welcome. We're backing up and reviewing Activity10.2B interior angle sums. Let's see. And in order to do that, you actually had to do 10.2A first. And the order of these was purposeful. And that was to play around with these shapes right here and find out what their interior angles measured. And so hopefully, I think I graded all of these that were submitted. You knew the interior angle of each of these. And they're mostly related to this triangle right here. So let's write on this just a little bit. So I hope you guys are okay with me doing a bit of review here. And then we'll talk about some of the new stuff. And again, this is fortunately a light week for us due to my inability to find, oops, that's the wrong book. Let's start a new notebook to find good online resources for the stuff in this section. We want a new document. What's this one down here? There's a new one. Okay, so for this one down at the bottom, let's move that up a touch. We could note that that's an equilateral triangle. And there was a video last Monday going over this one, equilateral and equiangular. And if something's equilateral and equiangular, what else could we call it? Anybody? My wife says I'm acting weird when she thinks it's the isolation. I'm not talking to enough people, so I really need you guys to talk back to me before I go nuts. If it's equilateral and equiangular, we can call it, starts with an R, E, G, U. Is anybody out there? Regular! Woo! Okay, and I see, Yazelle, you unmuted your mic, but I couldn't hear you. So you might want to test your mic if you want to talk. Do you know how to do the test mic thing in Zoom? There's a little arrow next to the mute button. And I think if you click that, it might bring up an option to test speaker and microphone if you have a mic. Otherwise, feel free to chat. Yeah, so this is a regular triangle. And regular means it's both equilateral and equiangular. So 2 of those together are regular. And so if it's regular, each of these angles has to be the same measure. And if we take 3 of these triangles and stick them together, so let's get to that app. Where's that app? Should be here. Let's go with Toy Theater. I thought that one was pretty cute. And I take 1, whoa, 2, 3 of these guys and stick them together so the angles, the vertices meet up. Come on, get close to each other. Sometimes the other one's better. Okay, so 3 of these equal angles make a straight angle, and a straight angle is 180 degrees. So I was looking for some play pictures as part of your evidence for these. Okay, so, oops. So in this case, we get 60 and 60 and 60 for this one. And so I could add to this, since 3 angles here add to 180, comma, maybe I could even go further, 180 over 3 equals 60. So, and again, we could say 2 triangles makes up this thing right here. So we get 60 and 60 and 60 and 60, 60 and 60. So coming around this way, we have a 60-degree angle followed by 120. And this picture could be your explanation. Sorry, that's not very readable. 60, 60, 60, 60, 60, when we split this into 2 equilateral triangles. All right. So kind of based on this picture, I was hoping you had a list of angles with some kind of reason or sketch as to why it came out that way. So moving on to the other one, this one, okay. So we have that experience with the pattern blocks. So now I want to use those to kind of come up with a quadrilateral and a pentagon and a square. And about half the class for the quadrilateral just said, well, the quadrilateral has 4 right angles. 4 right angles, 4 90-degree angles adds up. Well, not all quadrilaterals have 4 right angles, right? Quadrilateral just means 4 sides. So in that one, I would need a little bit more work. And so, for example, here, I might use for my, I need to copy this. So I can scribble on it. For my work on this one right here. And this is kind of my fault that it didn't go as well as yours, because I had started talking about it at the end of Monday last week, and then Wednesday asked if anyone had any questions on it, and nobody said they had any questions, so I just said, okay, and just moved along. So for example, here, I could note that the blue rhombus had 60 degrees and 120 degrees and another 60 degrees and another 120 degrees, which equaled 360 degrees. And then the orange square, another quadrilateral. And most people kind of gave a rectangle as an example, if not a square, would be 90 degrees plus 90 degrees plus 90 degrees equals 360. But then I was hoping you get a little more adventurous instead of just having one example there and play with the toys. So can we make another quadrilateral with these toys? Well, of course, we have that's another quadrilateral right there. And most of you figured out what its angles were. Let's see, this one right here has what? 1, 2, that has 4 sides. So the red trapezoid. Hopefully you got that in your previous ones. So let's add that to my notes. So red trapezoid. Moving around that one, if we start with one of the acute angles, we get 60 plus 120 plus, 120 plus 60 as we work our way around that sucker. So just double check back here. We can break this sucker into 3 of these equilateral triangles. And so then we get 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees, and 60 degrees there. So that this angle right here, this obtuse angle, we can see is 120 degrees. And the same thing here, that would be 120. So I was hoping you would connect these 2 together to kind of list some evidence here for this one right here. Now, the other thing I was hoping is you would remember reading about this in the book. And so the book says, okay, here's some polygon. This one would be here. This would not be what we call a convex polygon. This is called a concave polygon because these 2 edges cave in side of it. Another way to tell something is concave versus convex is if you connect two vertices that aren't already connected. That's called a diagonal. If you have an exterior diagonal, like if I connect point B to point F, that diagonal is outside the interior. That means it's concave, not convex. So here they give an example of cutting these three angles off and sticking them together so the vertices all meet. You get a straight angle, 180 degrees. And then further down, they say, okay, well, here's a quadrilateral, and this is kind of a random quadrilateral. It ain't a kite, it's not a trapezoid, it's not a parallelogram, it's just some quadrilateral that's not special in any way. We've talked about special names. And what they do is they draw a single diagonal and say, hey, look, this makes, whoa, I didn't mean to do that. Huh. The images, oops, lead to an image page. Oh boy, now I lost it. All right, here we go. Let me screenshot that sucker. Actually, I'm just going to make my own version of it, and I skipped past it somehow. No, that's the wrong section. All right, here's the section I want. Okay, so they show the quadrilateral, and then they talk about a pentagon and an octagon, and they give a solution here for a concave pentagon and a convex octagon. And notice they're not regular. And so there's nothing special about being regular except they have the same number of the same congruent edges and the same congruent angles. And so they're trying to come up with a formula here. And so basically this activity was the try it 10.2.2. And they have all the answers here. And my hope was that answer made sense to you based on the evidence. So we're gonna go through this evidence here together right now. So back to my notebook. And feel free to pipe up in the chat if I go too fast and lose you. All right, so based on these three, it seems like it's 360, right? Because 60, 120, 120, and 60 again add up to 360 degrees. Okay, so I'm gonna write 360 degrees. But I don't have a concrete reason here. I just have three examples of different figures. So I'm gonna go on the next page and draw some more about the quadrilateral. Wrong page. There we go. So I'm going to make two different quadrilaterals, just some kind of random quadrilateral. There's my quadrilateral. It has 4 edges. Oops, that's not a point. Let's try again. And 4 vertices. And I'm going to draw another quadrilateral just for fun. Let's make this one blue. And I think I talked about this one last week. This is like the Star Trek. I always get Star Trek and Star Wars confused. My apologies if you're a fan of either. My ignorance. I'm pretty sure this is the Star Trek logo. Is that right? Any confirmation from the live internet audience there? Yes, thank you, Kayla. Oh, speaking of Star Trek, I just watched Picard on CBS, and it was pretty good. I wouldn't say awesome, but it was pretty good if you're a Star Trek fan. All right, anyway, so this is a quadrilateral, right? It's got 1, 2, 3, 4. And what the book suggests is, and I brought this up in class on, I think it was Wednesday last week, if we look back at the recording, that if you connect a vertex that's not already connected to another vertex, so these two vertices right here and right here, they're called adjacent because they are connected by an edge. So this vertex is adjacent to that one. But this vertex here is not adjacent because they're not connected by an edge. But I can connect them if I want to, and two vertices that aren't adjacent are diagonal to each other. And so if I draw an edge inside here, that dotted line is a diagonal, as opposed to the green lines, which are edges. So if I draw and connect starting with a particular, that was supposed to be a star. Oh, that went bad. Try again. You got to pick a particular vertex, and I can't draw a star and talk easily, and then say, okay, I'm going to connect that vertex to every other vertex, right? Well, it's already connected to this one. It's already connected to that one. I just needed to connect it to that with a single diagonal. Once you take a single vertex and make sure it's connected to everybody directly, then you've split your figure into triangles. So here I have triangle 1, and here I have triangle 2. And what do I know about triangles? Well, I know if I take this angle plus this angle plus that angle, I get 180 degrees. And so now I have this other set of angles over here. I have this angle there, and I have this angle here, and that one over there. And all those lines make it look like they're congruent, which is a lie. So single lines. So I have these two original angles from the quadrilateral, and then the sum of these two angles from the triangles is now an angle, interior angle for the quadrilateral. Same thing over here. This triangle angle plus that triangle angle gives me this quadrilateral's angle. And I played around with GeoGebra with something like this last week. And I know that this triangle had 180 degrees in between these three angles. And I know that this triangle had 180 degrees between these three angles. Maybe I should color code those. Say this angle plus that angle is 180. And this red angle and the blue angle make an angle for the quadrilateral. This blue angle and the red angle make the quadrilateral. So I've dissected the quadrilateral into two triangles, and all of the interior angles of the triangles perfectly match the interior angles of the quadrilateral. So this tells me that the interior angle sum for this, any quadrilateral really, interior angle sum has to be 360. And we'll just confirm that over here. So we can pick any vertex. So this is vertex A. Let's call that one B, this one C, this one D. I need one of you to pick one of these letters. I'm just going to pick first. Any letter. A. Thank you, Olivia. So we're going to pick on vertex A. And vertex A here is already connected to D. And it's already connected to B. Shit, that's a bad choice. Sorry. Let me see. I think this is going to fail my demonstration, but I'm going to try it anyway. And let's see, I'm connected to B, I'm connected to D. If I try to connect to C, that gives me an external diagonal, and I need it to be internal. Okay, so I lied. We can't pick anyone we want. It's got to be a vertex that leads to an internal diagonal. So, oops, can't pick on A, and we don't want that diagonal. We got to pick on B or D. So we're going to pick on B. B is not yet connected to D, so we will connect it. And that gives me two triangles here. And I know that this angle plus this angle plus this angle is 180. And that is part of the interior angle sum for this quadrilateral. But then if I take this other triangle and take its three angles, I've now completed all of the interior angles of the quadrilateral. So that gives me another 180. So whether it's concave or convex, this is convex, and this one is concave, it doesn't matter, turns out. The angle sum for quadrilateral is 360. Okay? And these were pretty arbitrary. I just drew some lines, had 4 lines connect consecutively. So my further evidence is that any quadrilateral is what the book and I were trying to get at. Quadrilateral can be dissected into exactly 2 triangles whose interior angles. Anybody remember the other word for instead of interior angles that we call angles like this here? takers on that question. The book also calls an interior angle a vertex angle because it's an angle emanating from a single vertex. So they're also called a vertex angle. Yeah, so this is kind of the reason behind it. Any quadrilateral can be dissected into exactly two triangles whose interior angles match those of the quadrilateral. And so we get 180 plus 180 is 360. And it turns out there's really nothing special about a quadrilateral, so we'll check out a pentagon in two different ways. So pentagons are next one here. So first I'm just gonna go to, let's see, a new page, and then we're gonna use one of those apps. I'm gonna try the other app this time. Math Learning Center. And let's make a pentagon. So the easiest pentagon I can make here is like a house, where I take a square and set a triangle on top of it. Okay. And so let's snapshot that. To current page, please. All right, so here we're going to look at pentagons. Pentagon interior angle sum. And some people just said, hey, it's 540, and with no evidence. And so that was kind of a problem. The point was here is to kind of play around with those toys and find some evidence. So we know from our previous activity that we have a 90-degree angle, a 90-degree angle, a 90-degree angle, and a 90-degree angle. And the triangle has 60, 60, and 60. And so that means this particular pentagon has an interior angle over here of 150 and an interior angle over here of 150. Otherwise, it has 90, 90, and 60. So let's see, 150 and 150 is 300. 90 and 90 is 180. And then we have the 60 there. So 0, 4, 1, 3, 4, 540. So we can see this one definitely has 540 for the interior angle sum. And that's supposed to be a degree symbol over there. All right, can we make another one? And then we'll do the dissection. So let's see. I think I can make, what if I take that and stick a little hat on it? Does that make a pentagon? 1, 2, 3, 4, 5. I think that makes a pentagon. 1, 2, 3, 4, 5. Yeah, so there's another pentagon. And screenshot. So let's just double check this one. Current page, please. All right, so what do we get here for angles? Now remember that this shape could be made up of 6 of those green triangles. And so every vertex has 2 60-degree angles, so that means each of those is 120. So we have 120 there, 120 there, 120 there, 120 there. This right here is a single straight side right there. Those two match up perfectly into a straight angle. So the last angle is up here at 60. So this is the outline of the shape here. I probably should use a different color. I'm going to do that again in red. And use the line tool. So this shape has a single edge there. Next edge goes there. Next edge there. So this is a pentagon for sure. Where those two figures meet here is not actually a vertex because the angle doesn't change as I move through them. And so this angle at the top is 60 degrees. So I have a whole bunch of 120s. So 1, 2, 3, that's 400. And then 20, 40, 60, 80. And then 60 gives me another 540. Okay, so I have 2 of them I put together, give me 540. So now we're just going to make some random pentagon and see what happens. So some random pentagon up here. So we have 1 side, 2 sides, 3 sides, 4 sides. All right, so here's my random pentagon there. That's 5-sided. And then we need to make sure we have 1, 2, 3, 4, 5 vertices, just double check it is a pentagon. And then we have to pick on a vertex, so we end up with interior diagonals. So I wouldn't want to pick on this one like I saw before accidentally. That leads to an exterior diagonal. I need them to be inside. So I need to dissect, which means break it up on the inside. So I could pick, let's say this vertex right here should work. So I'm going to star that one. It's the one I'm going to pick on. And then I'm going to say, well, it's already connected there, but it's not here. So I need to diagonal that. It's not connected there, so diagonal that. And it is connected there. So if we pick on any vertex such that the diagonals are interior, then what should happen is if we connect it to all the other points it's not already connected to, so this is a dissection of a figure, then I get exactly 1, 2, 3 triangles. So there are 3 triangles in a proper dissection of a pentagon. So then 3 times 180 happens to be 540. So now we have a reason that it's always going to work out that way. So we have 2 examples leading us in that direction, and then this kind of takes us there. All right, so my hope was that, again, back here, that you use the Polygon tools here to kind of play around by making a quadrilateral, several quadrilaterals, some pentagons, hexagons, and it looks like I wasn't clear enough on that because a lot of people found the formula and then kind of made up some reasons that it worked here. All right, let's do the heptagon. That was rather a hard one, so I'm going to skip hexagon for now, and then that'll be enough evidence. And if anybody wants to go back and redo their activity 10.2, please go for it. So take a look at my comments and think about what I have here. So I'm going to try making a heptagon next. Where's my notebook? So heptagon. And so if you didn't know what that meant, you could look it up, or you might, I mentioned it in last week sometime, I can't remember if it was Monday or Wednesday, is a 7gon. It has 7 edges, 7 vertices. And so I'm going to try and make one with those toys first. And this I found to be a challenge. So I think I'll use the math one. Okay, so that right there, let's see, 7 sides. Well, how could I make 7 sides? This is a pentagon. And if I put another triangle on there, rotate, I think that's going to give me a hexagon. 1, 2, 3, 4, 5, 6. That's a hexagon, not a heptagon. If I throw another triangle on there. Oop. If anybody else has a better idea for making a heptagon, please let me know. All right, so this is now concave, not convex, but let's see if I start here. 1, 2, 3, 4, 5, 6, 7. Okay, that appears to be a heptagon. It's concave, not convex, and that's okay. Sometimes it matters, oops, wrong button, whether it's concave or convex, and some properties don't matter. It kind of depends on the property. Add to current, yes please. All right, so we want to know, and again, let's just double check by coloring vertices that this is truly a heptagon. 1, 2, 3, 4, 5, 6, 7. Yeah, it's definitely a 7gon. All right, so what do we have for angles then? We've got 90 and 60, which is 150. And then over here, we have 60 plus 90 plus another 60. I can't do that in my head. 60 plus 90 plus another 60 is that 210? 12 and 9. Yeah, I think that's 210. Double check, that would be 15 and 6 is 21. Yeah, 210, wow. This one up here is 60. 60. Over here, I have another 210. And over here, I have a 60. And this is going to be a 90 plus a 50, so it's a 1. 150. So 150 and 150, there's 300. 210 and 210 is 420. 60, 60, and 60 is 180. And 0, 0, carry the 1, 4, 5, 6, 7, 8, 9. It looks like the interior angle sum is 900. So let's go back to my notebook and see if this is making a pattern. We had 360 there. We had 540 here. We didn't do the hexagon, but if I look at the regular one back here, this was 60. No, that's a lie. 60 and 60 is 120. Those are the green triangles. And so for that one right there, that's going to give me on the regular 6 times 120, which is 720. Oops. So I proved that. I have one example of that, so I'd have to do a better job on that one right there. This is kind of sketchy. And then I have a single heptagon that gave me 900. Is there a pattern to these numbers? Ooh, I think there is. I think when I look at this here, to get from here to here, I add 180. And from here to here, I add another 180. And to get from here to here, I add another 180. And interestingly, 180 is an extra triangle. Oh, interesting. Okay, let's go explore that. Let's see, over to my picture. Next. Next. All right. Let's see, these were the pentagons. I want the heptagon. Ah, there it is. All right, so I'm going to try to reproduce that and just cut it up a slightly different way. So this has a line, and a line, and a line, and a line, another line. And it's not a great reproduction, but it will do. Okay, so here is my recreation of that heptagon. Oops, color blue. 1, oops, no blue, come on. 1, 2, 3, 4, 5, 6. Yep, it's still a heptagon. 7. And then I have to focus on one of these that doesn't lead to an exterior diagonal. So I wouldn't want to focus on this one because that leads to an exterior diagonal, because I want to dissect this, kind of like the book was telling me to. And let's make green dissections. So picking on this one right here, it's already connected there, but it's not connected there. It's also not connected directly here. And it's not connected directly there, nor is it directly connected over here. Okay, so that gives me 1, 2, 3, 4, 5 triangles. And so I need to figure out what is 180 times 5. So let's see, 5 times 0 is 0. 5 times 8 is what? 40, carry the 1. 5 times 1 is 5, plus 4 is 9. Okay, yeah, there's 900 using the dissection technique. All right, so now we have more evidence. So I'm going to put that down in my evidence back here. So a heptagon can be dissected into, to count again, 5, wasn't it? Yep, 5. And so I would want to, include that picture as part of my evidence. A heptagon can be dissected into 5 triangles. 5 times 180 equals 900. And I also have that other example that I did a different way. And then try the same thing for an octagon and see what happens. So let me see, this is what, 3-sided, 4-sided, 5-sided, 6-sided, 7-sided, octagon is 8-sided. The ultimate goal of this was to then come up with a formula for an n-sided figure. And so then I would just plug into the formula and out pops an answer. The book gives that answer. Most of you found that answer somewhere, either on your own or some other site, that's totally cool and no problem with that. I just was looking for some evidence for the other ones. And applying the formula is an evidence because the point is to, well, why the heck is the formula right? Like, where did it come from? And the book tries to go over that here. So again, they have why a triangle has 180. They have the dissection of a quadrilateral. And then they ask you to do a dissection of a pentagon and an octagon, and then extend it here. And then if you click here, you get the answer for this table and what the formula is. So if you didn't get a 10 out of 10 for this assignment, feel free to go back and resubmit some work for it. If you're fine with your grade, cool, don't bother, leave it alone. It's totally up to you. But please consider checking that out. Okay, so that was last week. I'm going to stop the recording there on that